Thank you for the introduction. I would like to talk about the interaction between spin currents and magnetization dynamics. This talk is based on these two papers. This is the outline of this presentation. First, I'll talk about the background of this study, briefly discussing about the interaction between spin currents and magnetization dynamics. And then, in this talk, I'll talk about two topics. One is an electrically tunable spin injector, and the other is a solution-processed organic spin charge converter. So first, let me mention briefly about the interaction between spin currents and dynamical magnetization. This is a schematic illustration of a charge current. As you know, a charge current is the flow of electron charge. But when two electrons with opposite spins travel in the opposite directions, as shown in this figure, the flow of electron charge is cancelled. But this flow of electrons creates a flow of spins. We call this a spin current. These equations are the continuity equation for electron charge and spin. This continuity equation for spin predicts that a spin current is coupled with dynamical magnetization by exchanging the spin angular momentum. A spin current is coupled also with a charge current through the spin-orbit interaction in a solid. This is known as the direct and inverse spin Hall effects. The direct spin Hall effect refers to a conversion of a charge current into a spin current due to the spin-dependent scatterings induced by the spin-orbit interaction. The inverse of this process, the inverse spin Hall effect, refers to a conversion of a spin current into an electric voltage. Using the direct and inverse spin Hall effects, we can generate and detect spin currents electrically. First, I'll show you what we can do using the direct spin Hall effect. Using the direct spin Hall effect, we can control magnetization in a macroscopic film. This is a sample used in this study. The sample is a ferromagnetic metal permalloy platinum, non-magnetic metal platinum bilayer film. In this film, a charge current flowing in the platinum layer is converted into a spin current through the spin Hall effect. Strong spin Hall effect in the platinum layer. And this generated spin current is injected into the permalloy layer. We have measured ferromagnetic resonance spectra with applying a charge current in this system and measured the interaction between spin current and dynamical magnetization. This is the experimental results. We measured the FMR signal. This is FMR spectrum as a function of the external magnetic field. We measured at two conditions. This is the data obtained when the external field is applied parallel to the charge current. And this is the data obtained when the external field is applied perpendicular to the charge current. What is important is that only when the field is applied perpendicular to the film plane, to the charge current, the spectral shapes are clearly changed by reversing the current polarity. To investigate this in detail, we have plotted the antisymmetric component of the spectral width as a function of the charge current, applied charge current. And as you can see from this figure, the spectral width increases linearly with the applied charge current when the field is applied perpendicular to the charge current. This demonstrates electric manipulation of magnetic damping because the FMR line width is proportional to the Gilbert damping constant. The origin of this damping manipulation induced by the spin Hall effect can be explained in terms of the macroscopic spin transfer induced by the spin Hall effect. This is a schematic illustration of a spin current under the precessing magnetization when the field is applied perpendicular to the charge current. At this condition, the spin torque acting on the precessing magnetization, which arises from the exchange of spin angular momentum between spin current and magnetization, is always anti-parallel to the damping torque. So this spin torque effectively changes the magnetic damping. This is the origin of the spin Hall effect induced manipulation of the magnetic damping. In this experiment, we have measured the FMR spectrum as a function of the external field. Actually, the FMR line width is clearly enhanced by simply attaching a platinum film. In the previous experiment, I showed you that spin injection into a ferromagnet changes the line width or changes the Gilbert damping constant. So this result implies that a spin current is emitted from the ferromagnet. If the spin current is emitted from the ferromagnet, we can detect the spin current by simply measuring the electric voltage induced in the platinum layer. Because a spin current flowing in the platinum layer is converted into an electric voltage through the inverse process of the spin Hall effect. So next we measured the electric voltage under the ferromagnetic resonance condition. This is the result. As you can see, this is a voltage signal as a function of the voltage. As you can see, a voltage signal appears at the resonance field. This is evidence that the dynamical spin as the precessing magnetization injects a spin current into the adjacent non-magnetic metal. This dynamical spin injection is known as the spin pumping. In ferromagnetic non-magnetic junction, the angular momentum of the precessing magnetization can be transferred to carrier spins through the interface spin exchange between the magnetization and the carrier spins. Next, I will show you that we can control this dynamical spin injection electrically by tuning the interface spin exchange coupling. That is an electrically tunable spin injector. The sample used in this study is a ferromagnetic metal permanently gallium arsenide junctions. We prepared two samples. One is a permanently gallium arsenide junction, permanently p-type gallium arsenide junction with a ohmic contact, and the other is a permanently n-type gallium arsenide junction with a Schottky contact. If the spin pumping injects a spin current into the gallium arsenide layer, we can detect the spin current, again measuring the electric voltage induced in the gallium arsenide layer, because the spin-orbit interaction in gallium arsenide is very strong. So next we measured the electric voltage under the ferromagnetic resonance for this system. This is the result. This is a microwave absorption signal as a function of the external field, and this is a voltage signal. As you can see, a voltage signal appears at the ferromagnetic resonance field. This is evidence that the spin pumping injects a spin current into the gallium arsenide layer through the ohmic and Schottky contacts. In fact, the electric voltage increases linearly with microwave excitation power, which is consistent with the prediction of the spin pumping. And also, this electric voltage changes systematically by changing the field direction. And this variation is very well reproduced using a calculation based on the spin pumping model. So these are evidence that the dynamical spin injection injects a spin current into the gallium arsenide layer. From the magnitude of the electric voltage, we can estimate the amount of spin currents injected into the gallium arsenide film. This is the summary of the result. What is important is that the spin current density obtained in these systems is comparable to that obtained in metallic system. So this demonstrates that the dynamical spin injection offers a versatile route to inject high-density spin currents into a wide range of materials. And also, one more interesting point is that the spin pumping conductance, which corresponds to the spin pumping efficiency for the p-type sample, is higher than that for the n-type sample. To investigate this in detail, we have measured the spin pumping and inverse spin Hall effect in a permanently p-type gallium arsenide junction with a Schottky contact. And the result shows that the spin pumping conductance for the ohmic type sample is again higher than that for the Schottky type sample. This result implies that we can control the spin pumping by tuning the interface Schottky barrier. So next we measure the spin pumping with applying a bias voltage across the junction. This is the result. As you can see, the electric voltage is clearly enhanced by applying a bias voltage across the junction. And what is important is that we found no change in the saturation magnetization, and also the electric voltage is not linear to the applied bias current. These are evidence that heating and magnetic galvanic effects in this system is negligible in this system. So this is also the evidence that the change of the electric voltage is due to the change of the spin pumping efficiency. From the magnitude of the electric voltage, we have estimated the spin pumping efficiency as a function of the applied bias voltage. As you can see, the spin pumping efficiency is decreased by increasing the Schottky barrier height and width. On the other hand, the spin pumping efficiency is increased by decreasing the Schottky barrier height and width. This is consistent with our intuitive picture that the dynamical spin injection is driven by interface spin exchange coupling between the magnetization and carrier spins. This is a demonstration of an electrically tunable spin injector. Let's move on to the next topic, the discovery of a solution-processed organic spin charge converter. Organic materials are mainly consisted of carbon and hydrogen and are characterized by the very weak spin-orbit interaction. In fact, the spin lifetime in these materials, the spin lifetime is basically dominated by the spin-orbit interaction. The spin lifetime in these materials is exceptionally long compared with other metals and semiconductors. So whether we can observe the spin charge conversion in such materials, in such weak spin-orbit coupling materials, is a fundamental and practical question. The answer we found is that we can observe the spin charge conversion in the solution-processed organic spin charge, solution-processed conducting polymer, P.PSS, in spite of the very weak spin-orbit interaction. And also we found that the long spin lifetime and high conversion efficiency from a spin current to a charge current coexist in this material. Let me explain this surprising discovery in detail. This is a sample used in this study. The sample is consisted of a conducting polymer, P.PSS, and a magnetic insulator, yttrium ion garnet. Yttrium ion garnet has been used as a spin injector in metallic systems, which shows a very small magnetic damping and a large charge gap. The use of a magnetic insulator as a spin injector allows to minimize the experimental artifacts in its measurements, such as the anomalous Hall effect and anisotropic magnet resistance in the ferromagnetic spin injector. Next, we measured the electric voltage under the ferromagnetic resonance condition for this system. This is the experimental result. This is the microwave absorption signal and voltage signal as a function of the external field strength. We measured with applying 9.4 gigahertz microwave in the cavity. As you can see, a clear voltage signal appears at the resonance field. I would like to stress again that yttrium ion garnet is a magnetic insulator. Nevertheless, the voltage appears in this system. So this clearly shows that the observed voltage is induced in the p-dot layer. So there are only two possibilities that can be the origin of the electric voltage. One is some electric effects, some electric voltage due to the microwave absorption, and the other is the spin pumping and inverse spin Hall effect in this system. But we found that the sum electric effects cannot explain the present result. There are two types of sum electric voltage. One is field-independent sum electric effects, such as the Zivik effect. And the other is field-dependent sum electric effect, such as the Nernst effect. To investigate the contribution from these sum electric voltages, we have measured the inverse spin Hall effect with a network analyzer and a coplanar waveguide, which allows to tune the resonance field by changing the microwave excitation frequency. This is data obtained using the network analyzer and a coplanar waveguide, measured at 6.5 gigahertz. And we can change the resonance field by changing the microwave frequency, as shown in this figure. And you can see that the experimental data is were reproduced using the Kittel's formula. First, the electric voltage due to the Seebeck effect should be independent of the field direction. But we found that the sign of the voltage is reversed by reversing the magnetic field direction. So this is evidence that the field independent thermoelectric voltage is irrelevant to the observed voltage. And secondly, the electric voltage due to the Nernst effect should depend on the field strength. This is the data. This is the voltage spectrum as a function of the external magnetic field strength measured at different microwave frequencies. As you can see, the electric voltage is insensitive to the resonance field. On the other hand, the Nernst effect predicts that the electric voltage is proportional to the resonance field, as this dashed line. So this is evidence that the field-dependent thermoelectric voltage is also irrelevant to the observed voltage. I have shown that the thermoelectric effects cannot explain the experimental results. So now there is only possibility that can explain the present result is the spin pumping and inverse spin Hall effect in this conducting polymer magnetic insulator junction. This is the microwave frequency dependence of the electric voltage induced by the spin pumping. A spin current generated by the spin pumping is proportional to the magnetic damping torque, which is proportional to the product of the microwave frequency and the solid angle of the magnetization precession trajectory, or the cone angle of the magnetization precession. This solid angle decreases with frequency. So the spin pumping predicts that the electric voltage is roughly constant with the frequency. The electric voltage is insensitive to the microwave frequency. When we plot the magnitude of the electric voltage as a function of the microwave frequency, the experimental result is well reproduced using the prediction of the spin pumping model. And we further studied the electric voltage by changing the field direction. By changing the external magnetic field direction, we can change the spin polarization direction injected into the p-dot layer. The spin polarization direction of a spin current is parallel to the magnetization precession axis, as shown in this figure. And this precession axis can be obtained from the relation between the resonance field and the angle of the magnetic field. This is the data, this is the result. This is the precession angle of the magnetization, and this is the field angle. As you can see, the spin polarization direction is almost parallel to the external magnetic field direction. So from the symmetry of the inverse spin Hall effect, the inverse spin Hall effect predicts that the electric voltage is proportional to a cosine function. As expected from this discussion, the electric voltage changes systematically by changing the field direction, and the result is well reproduced using a cosine function. So the symmetry of the voltage generation is fully consistent with the prediction of the spin pumping and inverse spin Hall effect in this system. So we have concluded from these evidences that the electric voltage is induced by the inverse spin Hall effect in the p-dot layer. By measuring the thickness dependence of the electric voltage, we can estimate the spin diffusion length in the p-dot film. The result is shown here. And using the diffusion coefficient, we can estimate the spin lifetime in this material, 8 microseconds. This is a summary of the result. The spin lifetime in the p-dot film is very long, as expected from the very weak spin-orbit interaction. On the other hand, the electric voltage due to the inverse spin Hall effect is only 2 orders of magnitude smaller than that of platinum, platinum is one of the most efficient spin charge converter. To understand this, the origin of this relatively large signal, it is important to consider separately two factors that influences the magnitude of the electric voltage. This is the electric voltage induced by the spin Hall effect, inverse spin Hall effect. Except for the geometrical factor, the spin Hall angle, which is the conversion efficiency from a spin electric field to the electric field, and the spin accumulation as a key factor for the voltage. The spin Hall angle defined as this equation should be small in the p-dot film because of the very weak spin-orbit interaction. But the very weak spin-orbit interaction in this film promises a large spin accumulation. This is the spin accumulation calculated from the Bloch equation with the spin exchange coupling. As you can see, the spin relaxation time is an essential parameter for the spin accumulation. In a material with long spin lifetime, it is easy to accumulate spins, which gives rise to a large spin accumulation. The spin lifetime in p-dot film is very long, so a large spin accumulation enabled by the long spin lifetime is responsible for the relatively large voltage. This is a summary of the result. The relatively large voltage in the p-dot film is induced by the large spin accumulation enabled by the long spin lifetime or the weak spin-orbit interaction. And from this data, we have estimated the spin Hall angle in the p-dot film, 10 to the minus 7. This very small value is consistent with the prediction of the weak spin-orbit interaction. The spin-orbit interaction in this material, the spin Hall angle in this material is very small, but I will show you that high efficient conversion from a spin current to a charge current is realized in this system. Because of the structural anisotropy, this material shows a large conductivity anisotropy. This is the in-plane conductivity, and this is out-of-plane electrical conductivity. In this measurement, a spin current flows along the low mobility direction, whereas a charge current flows along the high mobility direction. By taking into account this conductivity anisotropy, we can define the conversion efficiency from a spin current to a charge current as this equation. So the conversion efficiency is enhanced by the factor of the conductivity anisotropy from the spin Hall angle. The conductivity anisotropy in this material is very large, 10 to 5. So this gives the conversion efficiency from a spin current to a charge current exceeding 10 to the minus 2. This is a very large value, which is comparable to that of platinum. So our conclusion is that thanks to the very weak spin-orbit interaction and the unique electronic property of this material, a conductivity anisotropy, the long spin lifetime and high conversion efficiency coexist in this material. This is a summary of my talk. Thank you very much for your attention.